we're skipping 6.4. We're going to come back to that later, but now we're getting on to 6.5. And 6.5 is where things get interesting, because now we're talking about circular motion. The key idea with all circular motion is this, that we want to point the direction of the acceleration towards the center of the circle. As a result, then, we want to break up all the forces into components where we can analyze the part of the forces pointing towards the center of the circle, right? We have some motion, it's a circular, it's a curved motion. Acceleration is towards the center. The word centripetal, by the way, means center seeking. Centri, meaning having to do with the center, and then pedal comes from the Latin word petire, which means to seek. So it's the center seeking acceleration. And so some basic formulas that you should know, right? 2 pi r over t, 2 pi rf, and the period is the reciprocal of the frequency. That should all be reviewed. What we're talking about here is, at least for now, is uniform circular motion. I think we will get to some non-uniform circular motion. That's in 6.5b. But for now, we're looking at uniform circular motion, meaning that A equals v squared over r. That's centripetal acceleration, and it's a constant centripetal acceleration. The derivation of the centripetal acceleration equation, you can look at this if you want. You don't have to know how to do this one, so don't worry about that. But there it is for your perusal, if you like. The net centripetal force. Centripetal force is a net force. It's not an individual type of force. The centripetal force can be provided by the tension in the string, by friction, right? If you have a spinning turntable and a coin sitting on the turntable, a banked curve, right? A car going around a curve. If it's banked, that means it's at an incline, so the normal force is actually providing some of the centripetal force there. It could be a normal force, right? It could be if you're in the inside of like a cylinder, that ride where people stand against the inside of a barrel and it spins fast, the floor drops out. That's the normal force pushing on those people. Gravity, you can have a gravitational force holding a planet or a moon or a satellite in orbit, something like that. So now we're going to look at some applications of uniform circular motion. And so we're going to look at some different free body diagrams, some different views. So if we have a string, all right, string and rope problem. So the string is on, we have some mass at the end of a string. And so here the tension force is the centripetal force. So in this case we've got this circle. Here it is. Here's the object with the string. So in this case, here's the free body diagram. It just looks like this, Ft. So now the question is, what does it look like from the side? So when you're looking at it from the side, it's on the string like this. Well, from the side, that means that there is some force of gravity pulling down, and then there's some tension, this same tension here. So let me do Ft, is pulling that way. There's a question at the bottom, can the string in this scenario ever really be horizontal? The answer is no. There always has to be some vertical component to the tension in order to counteract the force of gravity. So no matter how fast this goes, it'll never be perfectly horizontal. So what are the plans here? Always draw a free body diagram, right? Always. Free body diagram or something like a free body diagram, even if it's not exact, because you want to look at the forces. You want to see what forces are involved. Resolve all the forces into radial and perpendicular to the radius accelerate tangential directions. In the tangential directions, right, the ups and downs, whatever, it's 0. In the radial direction, all the forces add up to m times ac, mass times the centripetal acceleration. And then you can solve for the unknowns. So here's another example, something a little bit more two-dimensional, and this is a conical pendulum. That's a conical pendulum, not a comical pendulum. It's one that's in the shape of a cone, not a pendulum that makes you laugh. So the side view here looks like this, right? And there's some angle theta here. Here's the tension. This is a tension force, and then you've got the force of gravity pulling down. All right, we're going to draw this again. But now what we're going to do is we're going to resolve this force. If I were solving this problem and I wanted to know, say, like, what's the tension in the string or something like that, well, what is the direction of the acceleration? As this thing is going around, right, it's a conical pendulum, so that means it's hanging and it's here. It's not swinging back and forth. It's swinging around like in a circle, and the string is tracing out the path of a cone. And so the center of the motion is this way. So I'm going to, this is going to be Ft Ft sine of theta, because theta's up here, right? We got to pay attention to that. And then this is the force of tension Ft cosine theta, up that way. And then this is the force of gravity. So if I know the mass, I can calculate what Ft cosine theta is, and then I can calculate Ft from that. Right? And this is equal to m times AC, mass times the centripetal acceleration. Okay. Next, if I have friction on a flat horizontal surface, what does that look like? So looking from the top, this coin or whatever it is on the turntable, it's going around, and there is a force this way, and it is a friction force. The coin, whatever it is, just sitting there, and friction is what's holding it in. If there was no friction, it would just slide in a straight line off. From the side, let's say if it's a coin or something like that, it looks like this. The friction force is pulling towards the center, and you've got the force of gravity equal to the normal force in magnitude. Okay. The next one, B2. This is now someone is stuck to the wall. And if they're stuck to the wall, the question is then, what's the force that's pulling them in towards the center? That would be the normal force, Fn. And that, of course, would be equal to mv squared over r. So we could do something like this, like what's the speed that it has to go in order for someone to stay on the wall. Okay, well, what are the vertical forces here? The vertical forces are the force of gravity, obviously pulling down. But what's the force then that's holding the person up, keeping the person from falling as the bottom drops out of this ride? And the answer is it's friction. It's a friction force, Ff. So that's mu, hopefully mu s, since they're not sliding, mu s Fn. You can see how you could calculate what v is, because this Fn is just mv squared over r. You calculate what v is from knowing what the force of gravity is, because this has to equal this. Okay, and so now this car example. Car with a banked curve. So it looks like this. Okay, and first we're going to look at this without friction. Okay, if there's no friction, that means that, okay, so what are the forces? We've got Fg pulling down this way. So the normal force is this way. So that's what Fg is, or Fn, right? This then is going to be Fn sine theta. And this has got to be Fn cosine theta. Right. Now notice what we're doing is we're doing the opposite of what we had done before, because before we resolved everything horizontal and perpendicular to the inclined plane. But here, since this thing is on a banked curve, right, it's coming around this way, and so this, what's the center of the circle? It's that way. This is the radial direction. So here's the direction of the acceleration, that way, right? I draw this off to the side, showing the direction of the acceleration. It's that way. So I resolve everything parallel and perpendicular to the direction of the acceleration. Now, what is this here, right? Fn, keep in mind that Fn is Fg divided by cosine theta. And so then this ends up being Fg tangent of theta. Right? And so then this is the centripetal force. And then now notice Fg is just mg, right? Mg tangent of theta is Fc. So that means that g tangent of theta is equal to v squared over r, or equal to AC in this situation. All right, so a little complicated there, but this is, you can see that you can keep a car on the track even without friction if you can get v to be the square root of rg tangent of theta. Now, C2, we're looking at this with friction as well. Now, whether or not there's friction, or what direction the friction is pushing, depends on how fast this thing is going, right? The free body diagram, so imagine here it's on the verge of sliding down. So what does this look like? Here's the car, and we've got the same forces we had before, Fg. This is Fn cosine or sine, this is Fn sine of theta. This is Fn cosine of theta. Right? We can figure that out by geometrical analysis, parallel lines, and all that sort of thing. And so now the friction force is pushing up this way, Ff, and here's the angle. So that means that the vertical part of this is going to be the friction force Ff sine theta. And then pushing this way is Ff cosine theta. But we're going to imagine here that it's on the verge of sliding down. So that means it's going slow. Since it's going slowly, sorry, what am I doing here? Yeah. Since it's going slow, friction is holding it up. And so then this is actually going to be Ff cosine theta that way. All right, and so now, what are all the horizontal forces? Well, Fn sine theta minus Ff cosine theta equals m AC. The idea here, again, if it's going too slow, it'll slide down. And this is showing it where it's on the verge of sliding. That means friction has to be pushing up on it that way. Now let's take a look at the other one. This is C2, but on the next slide. Here it's on the verge of sliding up. That means it's going too fast. It's going really fast around the curve. And if it goes any faster, it'll slide up that way. If it's about to slide that way, that means that the friction force is pushing it downhill. So that's Ff. This then, if I break this up, it'll be pointing down and that way. So this now is Ff cosine theta, and this is Ff sine theta. Keep this in mind, like for the normal, these two things have to be equal to each other. This equals this. If it's moving just in a horizontal circle, these two things have to be equal. And so now, Fn sine theta plus Ff cosine theta is equal to MAC. Okay. Let's go right ahead and move on to the next thing. So now if we have non-uniform circular motion, that means that the v could be changing. But v is still, the instantaneous velocity is still 2 pi r over t. And some examples of non-uniform circular motion would be a merry-go-round, Ferris wheel, some of these things, vertical circles, right? A lot of vertical circle things. Things like those are uniform. Non-uniform would be a roller coaster, a diving airplane, a bucket being whirled around. So recall elevator problems, like the monkey situation. If there's downward acceleration, that means there has to be a larger net force down than there is up, down versus up. And if it's accelerating upward, then there is a larger upward force than there is downward force. Again, this doesn't tell us the direction of the motion, just the direction of the acceleration. So here, that's the direction of the acceleration. Here, that's the direction of the acceleration. So let's think about this for a minute as the bucket is whirling and it's at the top of the path. Right, so here's the bucket. It's got a string pulling down on it. We want to know the slowest speed that it can have. So here's v. If that's v, the direction of the acceleration is down. The slowest possible speed, then, there won't be any tension in the string. It means if there's no tension in the string, the only force pulling downward on it is this, Fg. So if this is the only force, Fg is equal to MAC. This is providing the centripetal acceleration. So mg equals mv squared over r. M cancels out. And v is the square root of gr. Right? Or if we switch the g and the r, we get radical rug. Right, so that's scenario 1. Scenario 2, vertical circles and strings. Right, things that you should already know. If we have a mass at the end of a string moving in a vertical circle, a couple of things. It will always move faster at the bottom than at the top. Always moves faster at the bottom. Why? Because as it's coming down, it has gravity accelerating it downward. That means the tension in the string is greatest at the bottom, and it's always least at the top. So when we're doing these types of problems, always, again, draw the free body diagram. Break the vectors into centripetal and tangential components. Use sigma F equals MAC for the centripetal acceleration. And now we're also going to have some tangential acceleration, which we can calculate using sigma F tangential equals MA tangential. And we're just splitting everything up. So, let's see. What does this look like? The free body diagram then. So if I have a string going around like this, then this is the direction of the tension. This is the direction of the force of gravity. And so the direction of the acceleration is that way. Here's the tension. So I want to know, what I'm going to do then is I'm going to break up FG into some components here, right? So let's redraw this where we can break this down. Here it is. That's the tension and the direction of the acceleration. And so here's the force of gravity. If this is some angle theta, then this is Fg cosine theta, and this is Fg g sine theta, right? Going that way. And so let me redraw this again. So here's Fg cosine theta. Here's Fg sine theta. Again, where theta was the angle with the vertical that, it's making here as well. All right, so the net force, Fc equals MAC. And so this is T minus Fg cosine theta equals mv squared over r. All right, and what about the tangential? Sigma F tangential equals ma tangential. All right, and then this is the only force in the tangential direction, right? Fg sine theta. So, and Fg is mg, so mg sine theta equals ma tangential. This cancels out. So a tangential is just equal to g sine of theta. All right. So now we can take this and we can apply this. What if theta is 0 degrees? Theta being 0 degrees would mean that it's hanging straight down. All right. So in this case, a tan is 0. Right. And in this case, AC would be, let's see, so if this is 0, this would be just T minus Fg. Right. That means T has to be really big because it's counteracting Fg. What if it's at 90 degrees, right? So it's over here, like that way. Here, A tan is G. Oh, sorry, this would be over M, by the way. So A tan equals G in this case, because it's pointing down. And then the centripetal acceleration is just going to be T over M. Right. What if it's off to the side this way? Again, same thing. So these answers apply here and here. And what if it's at the top? Right, it's up like that. In that case, A tan is going to be, again, 0. There's no force. And AC is going to be T plus Fg, because in this case, they're both pulling in the same direction over M. Okay. All right. Vertical arc problems, right? All these are, again, just like elevators. If you have so the first one, if you've got the car going over a hill, or the roller coaster over a hill, or the airplane going over something, in that case, what direction is the acceleration? It's down, right? That means you've got the force of gravity, which is greater than the normal force. Or in the case of an airplane, it would be a difference of pressure providing the force. Okay, and then what about in the next one? So when we have downward centripetal acceleration, when you have an upside down roller coaster. The upside down roller coaster, there the normal force is actually pushing down, right? As long as it's going fast enough. If it's not going fast enough, then there's no normal force. It's like the whirling bucket problem we had before. And then what about when you're at the bottom of a curve? All right, if I have a roller coaster car or an airplane at the bottom of a curve, so something like this, like what's in the packet, in that case the direction of the acceleration is upward. That means that whatever the force of gravity is, the normal force has to be greater. So it's at times like this on a roller coaster where you feel heavier. If you're putting your hands up in the air, it's actually harder to keep your hands in the air at times like this because the seat is pushing up on you more and you feel heavy. What you feel actually is not the force of gravity. What you feel is the earth supporting you underneath, right? And the weight of your body on the bones. So when you're at the top of a hill on a roller coaster car, right, you actually feel lighter because the seat is pulling on you less, right? Remember this? What we just looked at, the normal force is less than the force of gravity. So you feel lighter than you are. Here you feel heavier than you are. All right, so let's take a look at this roller coaster car that's going around and up and down on a roller coaster, and it's going around. So the different points, we're just going to draw what direction the acceleration is. At point A, all right, it's coming around the curve, and so the direction of the acceleration is towards the center of the curve. That's it. At point B, it's at the bottom of a dip, right? Okay. So there, the direction of the acceleration is upward. At C, it's at the top of a hill, so the direction of acceleration is down. D, it's at the bottom of a dip, so the direction of acceleration is up. At point E, it's coming around the curve, right, going around the other side. So at point E, the direction of acceleration is to our left as we look at this. F, it's at the bottom of a dip, so the acceleration is upward. G, it's at top of a hill, so the direction of acceleration is downward. And then at point H, it's at the bottom of a dip again, so the direction of acceleration is upward. Okay. And the rest of this now is just looking at any other problems that we're going to see is using these free body diagrams and drawing the diagrams and writing the equations and using Newton's laws to solve. And they'll be combined in all kinds of ways. You'll be amazed at how complicated it can get. But just keep the basic ideas in mind. Draw the picture, separate everything into the radial and tangential directions, and set up Newton's laws equations, and you should be able to do it.